Welcome to this explainer, everyone. I'm absolutely thrilled you're here, because today we're tackling one of the most fundamental and sometimes totally head-scratching concepts in chemistry. Have you ever stopped to wonder what exactly forces a chemical reaction to just stop? Like, why don't the molecules keep on reacting until literally everything is gone? Well, today we're going to demystify that exact puzzle. To get a handle on why reactions don't just go on forever, think about baking a cake. Imagine you're in the kitchen. You've got butter, milk, and sugar in absolute abundance, but you only have exactly 1 cup of flour left. It really doesn't matter if you have 10 dozen eggs or a literal mountain of sugar, right? The very second you run out of that single cup of flour, your cake baking operation grinds to a sudden, screeching halt. Chemistry works the exact same way. One crucial ingredient always dictates the stopping point. So here's our roadmap for today. First, introducing the limiting reagent. Then the 4-step method. Next, solving multiple problems, tackling mass-based reactions, and finally, finding excess and yield. Let's get into it. Section 1. Introducing the limiting reagent, the reactant that runs out first. Okay, let's dive into this. The definition here is loud and clear. The limiting reagent is simply the reactant that runs out first. And because it runs out first, it holds all the power. The amount of this limiting reagent completely determines the maximum theoretical yield of our products. Just like that flour determined exactly how many cakes we could actually bake, the limiting reagent sets the absolute ceiling for our chemical product. You see, in stoichiometry, we're essentially always dealing with a fundamental duality. In one corner, you have the limiting reagent, the one that gets entirely consumed and just stops the show. And in the opposite corner, you have the excess reagent. This is the reactant that's left just sitting around in the beaker, totally twiddling its thumbs after the reaction stops, simply because it has absolutely nothing left to react with. Moving right along to Section 2, the 4-step identification method, a foolproof framework. All right, here is the foolproof 4-step method you're going to want to remember. Step 1, always ensure your chemical equation is balanced. Step 2, convert the given amounts of all your reactants into moles. Step 3, and hey, pay super close attention here because this is where a lot of folks trip up. Use your stoichiometric ratios. You do this by dividing the moles of each reactant by its specific coefficient from that balanced equation. And finally, step 4, identify the lowest resulting value. That lowest number points directly to your limiting reagent. Which brings us to Section 3, solving multiple problems, starting simple. Let's look at a true classic, the creation of water. Our balanced equation is 2H2 plus O2 yields 2H2O. And the problem states we're starting with 3 moles of hydrogen and 4 moles of oxygen. Now, since our equation is already balanced and we're luckily already in moles, we can actually just skip ahead and jump right to step 3 of our method. Breaking down the math here, we take our 3 moles of hydrogen and divide by its coefficient, which is 2. That gives us a ratio of 1.5. Then we take our 4 moles of oxygen and divide by its coefficient, which is 1. That gives us 4. Comparing the two, 1.5 is pretty clearly less than 4. So the crucial takeaway here is that hydrogen absolutely dictates this reaction. Hydrogen is, without a doubt, our limiting reactant. Now, what's really interesting about this slide is a clever little variation of this exact same water reaction. What happens if we flip the script? This time around, we're starting with 5 moles of hydrogen and 2 moles of oxygen. But the question is now asking us to find not just the limiting reactant, but also the excess reactant and exactly how much of it is left over. Walking through the math, we do our trusty division again. For hydrogen, 5 divided by 2 gives us a ratio of 2.5. For oxygen, 2 divided by 1 gives us 2. This time, 2 is the smaller number, making oxygen our limiting reactant, which means, by default, hydrogen is in excess. Since we know oxygen is the boss of this reaction, we use it to figure out the leftovers. That 1-to-2 ratio between oxygen and hydrogen means our 2 moles of oxygen are going to consume exactly 4 moles of hydrogen. We started with 5 moles of hydrogen, we used up 4, which leaves us with exactly 1 mole of hydrogen just sitting in the beaker, completely unreacted. All right, Section 4, tackling mass-based reactions, grams to moles. So what happens when we aren't handed nice, neat little moles, but instead we're given our starting materials in grams? Let's say we're asked to identify the limiting reactant in a reaction between 46 grams of iron and 32 grams of sulfur to form iron sulfide, or FeS. Notice the balanced equation we're working with here. 1 mole of iron reacts with exactly 1 mole of sulfur. It's a really beautiful, simple 1-to-1 ratio. But hold on, we can't just compare 46 grams directly to 32 grams. Remember step 2 of our framework? We absolutely must convert mass to moles first. It's crucial. So we take our 46 grams of iron and divide it by iron's molar mass of 55.85, and that gets us 0.82 moles. We do the exact same thing for sulfur, which gives us 0.72 moles. And only now can we finally make a fair apples-to-apples comparison. Because they react in that lovely 1-to-1 ratio, the stoichiometry step is incredibly simple. We just compare the mole amounts directly. We've got 0.82 moles of iron and 0.72 moles of sulfur. Since 0.72 is clearly less than 0.82, sulfur is our limiting reactant. It literally just has fewer available molecules to pair up with the iron. Let's bring it home with section 5, finding excess and yield, the ultimate goal. Okay, so we've totally mastered identifying the limiting reactant, but how do we actually find the tangible, real-world yield of our product? Take a look at this complex combustion reaction. What mass of carbon dioxide is formed when 20 grams of glucose reacts with 50 grams of oxygen? This specific problem requires us to synthesize absolutely everything we've learned so far. First things first, mass to moles. We take our 20 grams of glucose and divide by its molar mass of 180, which gives us 0.111 moles. For oxygen, we take our 50 grams and divide by its molar mass of 32, giving us 1.56 moles. The logic here is exactly the same as our iron and sulfur problem, we're just dealing with slightly heavier molecules. Now, we apply our trusted 4-step method one last time to find out who is limiting. The balanced equation requires 1 mole of glucose for every 6 moles of oxygen. So we divide glucose's 0.111 moles by its coefficient of 1, keeping it right at 0.111. Then we divide oxygen's 1.56 moles by its coefficient of 6, which gets us 0.26. Comparing those two ratios, 0.111 is definitely smaller. So therefore, despite having what really feels like a tiny amount initially, glucose is our limiting reactant. And this brilliantly illustrates our next step. Now that we know glucose is the one driving the car, we use only the glucose to calculate our final product. The balanced equation shows a 1-to-6 ratio between glucose and carbon dioxide, meaning for every single molecule of glucose we burn, we get 6 molecules of CO2. So we multiply our 0.111 moles of limiting glucose by 6 to find that we'll produce exactly 0.666 moles of CO2. The final step is just converting those moles of CO2 right back into grams by multiplying by the molar mass of CO2, which is 44. And ta-da! We get a final yield of 29.3 grams of carbon dioxide. By taking the time to find the limiting reagent first, we successfully unlocked the true, mathematically proven final answer. Which leaves us with this final thought for today. We've been looking at all of this through the lens of classroom math, just grams and beakers. But zoom out for a second. If limiting reagents dictate the absolute maximum yield of a product, imagine how chemical engineers must manipulate these exact same mathematical ratios in massive pharmaceutical labs or global industrial manufacturing plants to completely eliminate waste and maximize their profits. The underlying principles are the exact same, but the stakes, they're in the millions of dollars. I really hope this explainer gave you a rock-solid understanding of limiting reagents. Thanks so much for learning with me today, and hey, stay curious.